My name is Daniel, and I'm working as an Android and images infrastructure engineer for Facebook in London. And in this session, we're going to speak a bit about efficient image processing. And I want to share some stories and some of the challenges that we faced at Facebook when we addressed these topics for our billion active users. But before we really dive into that, let's talk a bit about what I'm not going to cover. So this isn't going to cover all the consumption experiences, all those steps where you want to download an image and display it in your app. And the reason for that is that we actually solved that already quite well as the Android community. And we went ahead and took all this knowledge and baked it into pretty great libraries, such as Picasso, Glide, or Fresco. But as the documentation correctly mentions, this only simplifies most of the challenges that we have when we deal with images on Android. And what I want to do is talk about the remaining ones. And one of the important bits is how do we prepare images before we upload them? How do we do those pre-processing of video? And the reason why this is important is because images are huge. If I, for instance, take a photograph from my Google Pixel phone, those are easily in the range of 4 megabytes. And if we have a panorama image, or if our smartphone manufacturer thinks it's a good idea to also embed another video inside our image files, then those files easily get to the size of 10 or 20 megabytes. So it's a good idea to make them smaller. And it's also easy to miss this, because if you test this on your office Wi-Fi connection, you see, oh, those upload quite fast and reliable, but as soon as you hit some lower network connections, you easily get into the multi-minute upload time. And that's not only true in areas where the network infrastructure is lacking, but that happens regularly. If you're in the countryside on a train, or if you're on a festival in a crowded environment. So how do we deal with this? And this is going to be the first step we do today on our journey, trying to reach the summit of efficient image processing, and that's trying to get those images a bit smaller. And one important leverage we have is we can decrease the resolution. So we take that original image and decrease the number of pixels. And those 3 images on this slide all decrease their side lengths by factor 2 with every step, which basically means the number of pixels decreases by a factor of 4. And this has a very profound impact on the actual file size that we're talking about. The other leverage we have is the quality parameter we pass to our encoder. And it's important to know that that quality setting that we often set, that goes from between 1 and 100, is not a percentage of quality, but rather just tells the encoder to either optimize for file size or for quality. And very high values can mean that you still lose quality and increase file size. And we talk a bit more about this later on how to choose these parameters in a good way. And probably the most important takeaway point of this talk, and probably if you should remember one slide, this is the slide, is that resizing has the biggest impact you can have on making your images smaller, and that twiddling with those encoder parameters is a good secondary step, but the first thing you should do is make the resolution smaller. And then there's the other question. So you then going into the conflict zone of how much resolution you upload, how much file size you save, and it's often that one size does not fit all. And what we, for instance, do in the Facebook app is we give the user the choice. You can choose to upload in a higher definition and accept that it takes up more bandwidth, or you choose a lower one. And it's also worth remembering that choosing those higher resolutions or lower resolutions is not only about speed and reliability. It also means if the people using your app are not on a flat rate data plan, they might just not want to afford those extra megabytes for uploading images, and are very happy if they have an option that they save a lot of data. So diving into code, and if you ever touched a bitmap on Android, you're probably familiar with this method. If you have your uncompressed bitmap, you can call compress on it, give it the compression format, the quality parameter, and a destination to save it to. And if you just want to go for a very simple example, this is what you probably would do is you take your input file, decode it into a bitmap, and then compress it again. However, we mentioned in the previous slides that we want to do resizing. So how do we do that? And the first step we want to do is we want to figure out how big is our initial image. And what we can do for that is we take the BitmapFactory and give it an extra parameter where we tell the decoder, hey, we're just interested in our dimensions. And that will tell the underlying JPEG or PNG decoder to just look at the header bytes and extract those values for us. And that goes very fast. And that's also a good trick that you can use to verify that the input data you're getting is actually an image. And then you can do that error handling right up front of your entire image processing. And then the fastest way on Android to get to a lower resolution is use sampling. And sampling tells the underlying decoder that it can skip certain pixels and never allocates a bitmap of the entire size of that image, but it performs a very efficient way of just getting a downsized version of your image. But it's also worth noting that on Android, the sampling parameters always must be power of 2, and we talk a bit about why this might be a challenge later on. And with those two methods, we then can go back to a transcode method, plug those two in, and we're done. And that's a very easy and efficient way to downsize your image. However, with the power of 2 step that I mentioned, it's very easy to overshoot or target. Imagine that your input image is just a few pixels larger than the maximum image size you want to get in the end. And then having to do those large steps will mean that you end up with an image that's just half the side length and quarter the resolution that you eventually want. And we talk about how we can deal with that in the next step. And that's going to be the second step we do. And that is about how to precisely resize the image. And the bitmap class has a static factory method where we can give it an existing bitmap, tell it a new dimensions for a new bitmap, and it will then create an exactly resized copy of that bitmap. If you're using the Kotlin extensions, you can also just call .scale on your bitmap object, and then you basically call the same method, it just looks a bit nicer. But for those who are stuck with Java in their projects, we're going to stick with the traditional APIs in this talk, but for the Kotlin folks, that's the extension packages are a really nice thing to look into, especially with image processing. And first thing what we do is we load our image into a bitmap, and then we can do the very easy check if that's already smaller than what we want to have in the end. We can just return and we're done here. And otherwise, what we want to do is we want to calculate what are the exact dimensions that we need in the end, and then call the aforementioned create scaled bitmap method. And also what we want to do is just before we return, we can recycle the original bitmap that we had just to put it back into that bitmap pool. And the good thing about this approach is that it optimizes for the maximum number of pixels with our target size, which is a nice thing because then we get a quite high resolution, but just within our target frame. However, what you might have noticed is in this approach, what happens is we allocate actually 2 bitmaps on the heap, and one of those bitmaps has a resolution of an input image. And if we think back of that 12 megapixel image they had in the beginning, that easily translates into 48 megabytes on the heap. And if you have an older phone, then this might just be enough to the device or your app and crash it for the user. So you don't want to do that. And what you can get around with is you want to have an approach that combines both of it. So you want to go halfway with the sampling and then just do the last bit with the scaling. So you benefit both from reducing the initial memory footprint of your first bitmap and then just do the scaling for the last bit. However, there's some more edge cases. So, for instance, if you can get away with sampling that is just below your target size, then you might want to prefer that approach of a scaling. And there are a lot of very fine bits in here, which is why I'm not trying to put that on any code slide here, but I just want to mention it that after you have your baseline with the sampling, this is the logical next step to do. So, and this concludes basically the first stops we had. So we figured out how we can efficiently resize and how we can go ahead and do a bit more interesting resizing. But if you ever done the steps and ever create an upload flow in your app, then you probably know this problem. So we did our resizing, we uploaded it, and all of a sudden, well, our image is turned sideways. And that's because the image files not only store the pixel data, but also metadata. It's usually in the EXIF format, and that might contain a field that tells us about the intended display orientation of those pixels. And what Android gives us is a very nice API, EXIF interface, where you give it the file to wrap around, and then you can just get and set those attributes for the different EXIF tags. And in our example, what we can do is, after all the resizing work, is we can go ahead, read the orientation from our input file, and then, depending on that, if it's not already in the up orientation, we can go ahead, try to calculate a transformation that usually comes as a matrix, and apply that to our bitmap. And what we need to handle is basically 8 cases. So we have 4 cases for all the quarter turns that you can imagine. And then we have additional ones which are for the flip variations. And that's often used by device manufacturers for the front-facing camera, because then they can very easily just mirror or demirror the image depending on what kind of capture you're looking for. However, in this approach, we also end up with 2 bitmaps on the heap. And either way, what we can do is, if, for instance, our output image is also a JPEG file, is we can just go ahead and copy those metadata over, because then we just work on our pixel data, do all the scaling, and then copy over the metadata with the orientation. And what we can also do at that point is look at the other metadata. And for instance, if you later want to display the user images on the map, then you might be interested in also preserving the location and the capture times. And to conclude this small stop is that EXIF interface, after the initial surprise that you might have when your image looked quite wrong, is actually quite easy to use and integrate. However, what it also means is that you have that second disk access, or you need that second bitmap on your heap. And especially if your pipeline gets longer and you do a lot of intermediate steps, then that might add quite some complexity. So we solved the metadata part. What could happen next? And you might end up with this. And I'm not sure if it shows correctly on the screen, but the second image that we get out looks a bit off. So it's a bit less saturated, a bit darker. So what's happening here? So besides the metadata that I mentioned, your image file also stores a color profile, which explains how to interpret the data it has. And what we can do on Android 26 and above is we can tell our decoder to automatically convert that to sRGB for us. And then when we save it back into JPEG, all that information gets lost, but every decoder will default to the sRGB color space, and then at least it will display correctly. If you, before 26, you're a bit out of luck, and there's no easy way to do that. And this is an often overlooked problem, because if you have certain phones, it might not even display correctly as a problem for you, and it's usually the more professional photographers that come to you and tell you that their colors are a bit off. And the other problem is that there is no simple backward solution yet for all Android devices. Cool. So we made quite some progress on our way to the top. And with every good journey, there might be the point where you question yourself, are we actually working in the right direction? And is the approach that we do the right one? Is it actually necessary that we always go and get our bitmap? And to further discuss this, let's have a look how JPEG actually works. And if you ever had a low-quality JPEG image, or you zoomed in a bit, you know there's this grid structure of these blocky things that have these weird artifacts on the borders. And basically what JPEG does, it takes your RGB pixel data in those blocks and transforms them over into another representation. And that representation is more like coefficients or frequencies, but that's not important. That's not a detail that we need to know. The important bit is that those blocks are actually independent of each other, and we can leverage that. And if you ever worked on a backend system, you might know the tool JPEG-Tran. And JPEG-Tran does actually leverage exactly this insight that we have those independent blocks. And because of that, it can do transformations on that block level without ever going to our bitmap and RGB world. And we can rotate the pixel data, we can crop the image losslessly. So if you have any cropping flow in your app, then this is a very interesting thing to do. And you can also change where in your stream the different coefficients appear, and by that change between a baseline JPEG and different variations of progressive JPEGs. And what this gives us the opportunity to talk another important thing, and that is minimizing re-encodings. And that should be one of our highest principles whenever we deal with images, because every single re-encoding, no matter what quality we choose, will always hurt our final quality to file size ratio. And so all those lossless transformations are a very good way of making sure that we minimize those re-encodings. And if we look deeper in those native libraries, and we dig a bit deeper, we see that, for instance, the libjpeg turbo library allows us to do a bit more precise sampling / resizing. And we're no longer bound to the power of 2, but we can go more precisely. We can go 1/8, 2/8. And that might allow us to get rid of the precise resizing altogether and just live with that very fast and very efficient decompressing. And also what we can do is we can go ahead and no longer take the entire image into memory, but stream it and just read portions of it and go with those. But you might have guessed that ends very quickly in a lot of C++ code. And I think slides like this make us all very happy that we usually can work with Kotlin and we don't have to deal with this. And this is one challenge you will face once you want to do more profound image processing, that you have to deal with native code. But this comes with a lot of challenges, and those challenges very often manifest in bugs. So you're losing compile time guarantees because your Java and your native code all of a sudden compile independently of each other. And you end up writing a lot of abstractions in glue code because Java and C have very different ideas how to manage lifecycle and memory, and also makes your testing harder. You no longer can just fire up RoboElectric, run test locally on your machine, actually needs to run on an emulator or real device. But it's also good to see that there are better solutions to our problems. And this is something we can leverage if this is a very important part of our app, if this creation flow is important to us. But it's also important to bear in mind that this adds a huge cost, and we pay these improvements by writing native code and having to maintain that. And another interesting example where this can lead us is the next point. And what most apps do is they not simply back up images, but they allow our users to express themselves. They allow you to get creative, add overlays. I'm not particularly good at that, but it explains the principle. But if we then go ahead and we look at our output image, let's first talk about how we actually get there. What Android allows us to do is we wrap a canvas object around a bitmap, and then we can call different draw methods on that. And the only important bit that I want to make sure is that we either work on a copy or make sure that the original bitmap is mutable. And with the Kotlin extensions, although this got easier, so directly on your bitmap, you can call an apply canvas method, and then just you specify a block with all the different drawing commands you want to do. So this is a nice way to save a bit of that boilerplate code. However, what you will see is our JPEG artifacts got worse. And especially on the boundaries where different colors change, we would get a lot of very colorful and noisy artifacts. And why is that? And that's another good motivation to look, well, what happens with image codecs? What happens when we compress? And what, for instance, JPEG does, and many other codecs, is when we take that RGB data and we leave that world, what we actually do is we split it up into one luma component and two chroma component for the color information. And the idea is that our eye is less perceivable for color changes, so JPEG actually stores those as a lower resolution. And that works pretty well for photographs, and that allows JPEG to compress images quite well. However, we then have this problem that color information is gone. So what we can do is we can tell our encoder that it shouldn't do that. So we just tell it, oh, don't resize our image, our color information, please. And that, again, brings it back into the native world. But it is just one more example where it might be worth going that extra mile to get the improved results. And what we did now is where we talk a bit about different steps we can do that hopefully improve our quality. But as every good engineer at this point, you might be questioning, is it actually worth it? And what's important whenever we do any optimization is, of course, to measure it, because otherwise we don't know which direction we're actually going to. And for image quality, there are basically a handful of metrics where we can measure quality, and they're usually reference-based. So what we do is when we take our input image, we take what we get out of our processing, and then we try to determine how much of a difference this is to the human perception. And probably the most common one that we talk about is MSSIM, and that stands for multi-scale structural similarity. And as the name maybe suggests, it has a quite academic, sound, and good mathematical foundation. But basically what it does, it goes over both images and works with derivatives of contrast change. And the multi-scale part just means that we execute it multiple times at different resolution, and by that simulate that a viewer might have a different distance to our images. And in the Android world, you often also see a butter ugly, which generates a similar code, similar result, but uses different underlying principles to get there. And what we then can do is we can draw funny graphs. So on the y-axis, we might put a quality metric where higher values means better quality, and on the x-axis, we put the file size. And here what I'm going to use is bits per pixel, so we get rid of the resolution, and we can argue independent of that. And if we take, for instance, a sample image and run it through a JPEG compressor, we might get a curve that's a bit like this. So in the beginning, we see for every bit that we spend on an image, we get a lot of quality improvement. And then there's a spot where we reached already quite good quality, but we still get good return. And then there's a long tail where no matter how much more bits we spend, those returns are quite diminishing. And usually for JPEG, where your sweet spot is somewhere in the range of 75 and 85. That's the range where you already have a good quality as a baseline, but still get good return on the bits that you spent. And what you can also use this graph for is you can compare different implementations. And one popular is Mozilla JPEG, which was released by Mozilla 2014. And the only thing it does different is in the encoding step, it just spends a bit more time and resources on finding better parameters. And the output it creates is still a standard conform JPEG file, which is very convenient for us because we can give it to all of the clients we have out there. And if we go ahead and draw it in the same graphs where we see it's all shifted a bit to the left, and that means at the same quality, we only spend a lower amount of bits. And that's something that's very interesting. And for the sample set of images where I run this on, what we ended up is having a 15% improvement. And that can mean a lot for people in areas with low or with high upload failures. Cool. So we made our way to the top. We figured out how to measure what we did, but let's take that time and have a look around. Let's have a look, well, what else is there? And if you followed the news, then you probably read about the high efficiency image file format, or short heap. And basically what it allows us is to use the keyframes of a video format and use that for images. And it was initially becoming part of the discussion when Apple announced it for their iPhone, but from Android Pie onwards, we also have support on our Android devices, and you can just use your normal BitmapFactory or with Android Pie, even image decoder to read those files and display them. However, if you want to create some, you have to do a bit more work. So what you need to do is you add the heap support library, then instantiate your heap writer, and then you can go ahead with that heap writer and add those image information. And there's a reason why this isn't as easy as your bitmap.compress, and that's because the codec is reusing the parts of the hardware that's actually already dealing with the videos. So the heap writer has to manage the allocation of those resources. And it's also important to notice that then the implementation depends a bit on the device, which makes deterministic statements about the quality a bit harder. And so, for instance, your set quality usually has a lower sweet spot than JPEG, but it also depends on which implementation the device is using. The other one that I'm personally quite excited about is AVIF. Sounds similar and has a similar idea. So instead of the HEVC codec, it uses the AV1 interface. And it's a standard that's currently in development, and it uses all sorts of new coding tools such as chroma prediction, interblock prediction, and basically what it gives is a much improved performance. And on a sample set that I run with our images was that it would go down to just 1/3 of the JPEG file at the same quality. But this is nothing that's available yet, and that's something that will take its time to make sure. But it's also, at least for me, super exciting to see that there are new formats coming up, and formats coming up that can make a profound change on how we deal with images and what kind of content we can deliver and how people can express themselves. But a word of caution with all those new image formats, and it's very tempting to go ahead and make use of them, but it's important to know the entire journey your image does. And just because you have the chance to use a new image format at some parts of the pipeline, if in the end you're still going to re-encode as a JPEG because your clients can't read those new image formats, then the only thing you really get is one additional re-encoding step along the way. So be cautious with all more modern image formats and all the things you might say that are very tempting to try out. Think about who is creating the image in which situation and who is going to consume that image, and how can you make this entire journey a nice, holistic approach. And you see this mountain one or two more times. What we did is we had a lot of stops along the way, and this usually doesn't go as smooth, but you learn by failure, you do mistakes, and what you might find out, it's quite hard to maintain, and what happens if you get another mountain? You have to climb this entire way again, you have to re-implement all this again, and that's a big challenge when it comes to trying new techniques and trying to deliver them in a maintainable way. And perfect image handling is hard, and I think there's no shame when I say that we also broke EXIF orientation at multiple points, that choosing the right compression parameters is hard, and it's hard to make it work right for everyone. And we saw also a lot of feature engineers struggling with this and trying to go that way on their own. And instead what we did is we thought, well, hey, we're nice people. We built you a little chairlift, so you don't have to go that way yourself all the time. And for software engineers, that basically means we went ahead and we built a software library. And what we decided is we make it declarative. Well, that sounds very hypey. What we mean by that is that instead of you having to know all the different things you have to do along the way, just tell us what you want to have in the end, and we deal with that. And that also allows us to be the ones with the knowledge of making the decision. That allows us to go ahead and, are you doing this transformation and we know a very cool new approach for this, then we can just implement that and you directly benefit from it. And also declarative interface means it's very easy to write tests because your call to the library basically describes what you're expecting, and then you just have to match against that. And also it keeps all those native and C++ code far away from all our product developers. We are not very keen to deal with that anyway, and they let us deal with it. And also allows us to test our changes globally. So on our library level, we can go ahead and test different encoders and different techniques just as plugins. And because we already deal with so much C++ code, why not move the entire thing behind a smart wrapper, and then also benefit from the fact that we can just reuse the entire work that we've done on iOS. And this is basically how it looks like. And it looks quite a bit different from what we've seen in the previous slide. So you just say, this is my input file, I want to create this output file. And the thing that I'm interested in is that whatever you give me in the end is a JPEG file, and the size is not exceeding 2,000 in each direction. And if you need a quality parameter, then choose 85. And then, for instance, someone goes ahead and just says, oh yeah, I want to have a JPEG file and please rotate it by 90 degrees because the user said, oh yeah, we need to switch between portrait and landscape. Then the library is smart enough to figure out, oh, this is an operation we actually can do lossless and that runs much more efficiently. And then it uses the underlying JPEG trend tool. And the same goes when you, for instance, have a bitmap and you try to write that down. Remember our overlay example? Then the library would already have, for instance, Mozilla JPEG implemented, and that gives us a much higher quality. And the feature developer doesn't need to care about, but directly benefits from this. And then if the feature developer, for instance, knows, oh, I have overlay, then they can just go ahead and tell us, oh, this chroma sampling that you usually do, please don't. But they never need to read any documentation about the underlying libraries or how this is different between different image formats. And this was a lot of content, and I'm aware of that. But it's just one sample journey up the mountain. And there are a lot of other different techniques that we deal with when it comes to image processing to make sure that we deliver high-quality images and also allow people to express them in a reliable way. And I want to use this chance, because we talked a lot about production, to point to two other image talks this afternoon, which are Image 101 by Effie in room 3, and Jake and John are going to talk about Picasso 3.0, and those are probably interesting if you want to see the other side on how to then process those images and display them back to the user. I think we probably don't have time for many questions, but definitely feel free to grab me after the talk. I'm also going to be at the Facebook and Instagram booth. And thank you all very much for coming here.